Welcome, everyone. I think based on the number of registrants, we'll have some people joining for a little bit, but welcome to Maximizing the Utilization of GPU Resources on Premises and in the Cloud. That's a long title for a simple webinar. We're excited to talk about GPUs today, and we've got a fun-filled agenda. We're happy to have the NVIDIA folks joining us here. And before I go through the introduction, why don't we just have each of the presenters introduce themselves, starting with Barton.
Hi, can you hear me okay?
Absolutely.
Great, thanks Rob. This is Barton Fisk. I'm a Senior Alliances Manager in the NVIDIA Tesla Platform Alliances Group. I focus on the HPC toolchain, including compilers, developers, schedulers, and the like, and I'm pleased to be with you today.
And I'm Adam Tettleman from NVIDIA. I'm a solutions architect, and I focus on deep learning and scaling out data center infrastructure and scaling up and maximizing your GPU utilization for AI workloads.
And Bill.
Hi, I'm Bill Bryce, the VP of Products here at Univa for Univa Grid Engine and for NavOps Launch.
Thanks, everyone. So I'm Rob Lalonde. I'm VP and General Manager of Cloud here at Univa. I'm just going to kind of kick things off and then turn it over to the smart people to do the talking. So this is the welcome and introduction. We'll quickly hand it over to Barton in a couple of minutes to tell you what's new at NVIDIA. Lots of exciting stuff. Adam's going to go deep on MEG, the multi-instance GPU technology, as well as the new A100 technology. I'm excited to see that myself. And then Bill's going to talk about what's going on in the workload space, particularly around Grid Engine, and how we're integrating with Docker and NVIDIA, and really to the benefit of our customers with all the GPU activity they've got going on. And then we'll wrap it up with some questions, hopefully from the audience. Have your questions ready, throw them in the chat, and Neil will get those over to us. And just quick advertisement before we get going. We're with Univa, Bill and I. We've been in the workload management and more recently the HPC cloud migration space for quite some time. We're excited to have Barton and Adam join us here from NVIDIA. Univa's, as I said, we're in the workload management space. Probably a lot of people know us for the Sun Grid Engine product, which has been around for many, many years and is a mainstay in HPC. We've been doing all kinds of modernization effort around that to support things like GPUs, and our customers in turn are doing some super cool things with that. And more recently, we are announcing we were just acquired by Altair. So Altair is obviously a very large engineering and software firm, and doing a lot in HPC. And I think this acquisition is going to be fantastic for our customers and for our products, and gives us a lot more resources to move things forward to everyone's benefit. And there's a lot going on with GPUs at Altair too, with all of the great solvers and data analytics tools and such like that too. So we'll talk about that another time. But certainly we did a survey this year on what was going on with GPUs in our market space. And you can see if we start over on the left, 83% of our HPC customers that are responded are relying on GPUs for some of their HPC applications. So that's pretty significant utilization. And I think the production item just to the right of that, showing how many of those are in production versus limited use or pilots, also speaks to the prevalence and penetration of GPUs into the HPC space. So really significant upticks from what we've seen in previous surveys. In the middle of the bar chart in the green, you can see a lot of people running machine learning, deep learning, AI workloads, but also running visualization, life sciences stuff, CFD stuff, structural stuff. That's the mainstay of a lot of the Altair applications. And you can see that 80% of these users running 3 or more distinct GPU workloads. So not just one application or another, but really relying on it for numerous different workloads as they go forward. The GPUs, these workloads are running both on-premise, on desktops, and in the cloud. So fairly balanced usage there, with the cloud being maybe more significant than I would have expected at this stage of the game. So lots and lots of activity there. And you can see what's happening with the public clouds and workload managers, and how the breakdown of different container technologies is happening as well with GPUs. You can see 33% using Singularity, which is probably not something you would see in the traditional marketplace, but certainly Singularity having a strong foothold in in the HPC space. So that's what we're seeing in the market. We're really excited about it, and probably more excited about what we see our customers actually achieving with GPUs. So having said that, I'd like to turn it over to Barton to tell you what's new at NVIDIA.
Great, let me grab my screen here. Should see my background.
Yeah, there it is. Fancy.
Yeah, and then should have our cover slide.
Yeah, great, go ahead.
Great, thanks so much. Well, hey everybody, great to be with you, and thanks for the opportunity to Rob and William and the team, and Neil, who's been corralling all of us over the last couple of weeks. Fun fact, actually, I heard Rob say SunGrid Engine, and so I'm gonna share that I once was the SunGrid Engine co-product manager many moons ago. So Univa and the Grid Engine technology has a deep place in my heart, and the spirit of a lot of that innovation and what happens in bringing these sorts of products to market is alive also at NVIDIA. Wanted to really just give you kind of a retrospective of what's new from NVIDIA from, let's say, announcements starting as far back as spring through the current time frame that we're in. We just closed GTC, which is a GPU technology conference, last week. So I'm going to walk you through a couple of major announcements, and then I'm going to transition over to Adam, who's going to do a bit of a deeper technical dive on where we are with state of development in GPUs, or specifically around workload management. So we've completed and closed the acquisition of Mellanox. This is a great contribution to NVIDIA, and literally every week I'm joining multiple different groups and different calls, helping them on board, helping them figure out how we go forward together. But overall, I just couldn't be more excited about having a chance to work with this technology and with the people that are part of that company. So it is completed, and we're building great products together, some of which you'll see in some of the future slides. So at GTC Spring, also around that time frame, we announced our next major GPU architecture under what we call the Ampere name, the Ampere family. A huge leap in terms of capabilities across the major swaths that NVIDIA addresses, which is compute, visualization, as well as analytics. We've literally moved the bar in terms of what's possible, both in terms of realism as well as capabilities in floating point computation. Along the timeframes of ISC 20, which was in the June timeframe, we've also released what we're calling the NVIDIA HPC SDK. In previous years, you may have seen that NVIDIA had acquired the PGI compiler technology, and over the last 5 years, we've essentially blended that set of technologies into our existing software tooling. And so seemed like now would be a good time, given all of the HPC hardware and software activity, would be to rebrand that and bring that tool set into the current sort of current environment that we support. So there's links here. These slides will be available after the talk with the links embedded. This will take you to a number of additional places to get more information, but just want to take the opportunity to let folks know that PGI didn't go away. It's been rebranded in the NVIDIA HPC SDK, along with all of the existing compilers, libraries, math libraries, and other utilities for developing HPC applications and deploying them at scale. So more recently, just in this last week, we held the online fall edition of GTC, had a great lineup of sessions and talks. Some of the work that I do, in addition to supporting the compute side of things, I'm also working on GPU direct storage. So we had a great opportunity to share current progress with GPU direct storage in that week. And as you probably recently heard, NVIDIA has announced an intent to acquire ARM, which we really view as the premier computing company for the age of AI. Unfortunately, right now, I won't be able to say a whole lot more about this. Please refer to the NVIDIA website for additional details and contact information. And we'll be keeping folks up to date as this progresses. The NVIDIA acquisition probably took better part of a year. And so over the coming quarters and months, as the progress of this acquisition unfolds, that'll be available through the NVIDIA website, as well as the ARM website, I would believe. But I want to drill down a little bit more in terms of how, as GPUs get more and more widely adopted across data centers, not just in research centers, but also in enterprise deployments, we're beginning to see the data center as sort of the new unit of computing in terms of different implementations, either in scale up or scale out or microservices embedded within. Some of the areas that I'm working on include the Magnum IO stack and some of the discussions we're going to have today around MIG, the multi-instance GPU capability that's in the Ampere architecture will be addressed by Adam. So another announcement from this week, the DGX SUPERPOD. This is essentially a turnkey, ready to go, let's say, building block for those aspiring to make it to the HPC top 500. We have taken this concept and actually built it into a supercluster of our own that we refer to as Selene, and that has been rated at number 7 on the top 500 with a collection of superpods to accomplish that. So this is just taking the idea of scaling GPUs literally to the lunatic fringe at this point, as well as the interconnects and the data paths to connect them. And when I saw this, it just looked like the perfect sandbox for someone to deploy grid at a massive scale, perhaps larger than a grid engine, larger than it's ever been. I know they've done some pretty impressive stuff on a couple of cloud deployments, but to have your own private cloud that you could just start issuing Q-sub commands is pretty appealing. Some labs and customers that have adopted this architecture, including Argonne and the Clova and Navier systems. The University of Florida is actually going to become one of the largest educationally centered research clusters, and has actually been made possible through partial funding from one of our engineering founders and leads, Dwight Dirks. Excuse me, no, not Dwight. That's not Dwight's. That's Chris. Yeah, that's Chris's. Dwight had invested in a cluster quite heavily in his alma mater up in University of Wisconsin in Madison. So to summarize quickly, we're really addressing the problems of computing for the age of AI. We've made additional strides towards coming up with, hopefully, theoretical contributions for vaccines for COVID, additional software investments for doing speech recognition. The NVIDIA Bluefield DPU and Docker announcements encourage you to go into the GTC materials when they become available online. They should be available towards the end of this month if you didn't already attend, as well as announcements we made with VMware and the push towards developing reference architectures for edge computing. And then sort of rounding out along the bottom there, announcements with Mercedes-Benz for their S-Class next generation autonomous vehicle technology, and also innovations in robotics along the Jetson and the embedded Tegra GPU lines. All of this potentially, these designs are able to be visualized in a collaborative metaverse that we call NVIDIA Omniverse. So I've thrown a lot of terminology, a lot of things here, but this one slide, you can double click for hours on each one of these topics. So if any of these interest you, please feel free to either get in touch directly or hit our website and we'll help you find the product teams that are relevant. So I want to also just peel away a little bit deeper from just the announcements and what we've been up to in the last 6 months, and talk a little bit more about, I think, things germane to you and to our mutual interests. And it has to do with provisioning of GPU accelerated infrastructure. And over the years, and the slides that Rob was actually sharing at the start really speak to this, that the traditional infrastructure has pretty much matured to the point where there is a ready supply of people familiar with how to deploy and maintain these systems. But we've seen in the past 5 years, as these systems benefit from the increased computational ability of GPUs, that doesn't necessarily mean it's easy anymore. And so some of the solutions that NVIDIA has been coming up with to address this include turnkey systems that can be deployed at scale. The DGX pod being an example of it, which is built up originally of DGX servers that were brought to market over the last 3 to 4 years, including the DGX1 and the DGX2, and the developer station, what we call DGX station. As well, we've developed automation tools to address issues of agility when dealing with large numbers of moving parts and pieces. And then most recently, in the A100 GPU in the Ampere family, we've brought what we call multi-instance GPU capability into the product line to help address finer-grained access to GPU resources. So thinking about a typical infrastructure for computing, this is kind of the old world and the way that things have traditionally been done, including just provisioning the infrastructure, and then if going through a virtualized infrastructure approach, putting in all the actual software pieces, the licensing, and doing effectively the burn-in and scale testing to know what that cluster is actually capable of. Then adding the cluster setup software and deploying applications all the way out to keeping the life cycle going as affordably as possible and dealing with hardware failures, as well as planning for ever-shifting roadmaps. On top of this existing sort of way of doing things, there's now added complexity having to do with the inclusion of diverse AI training and deployment environments. So we broadly categorize AI workloads by either development, where you're testing and proving out ideas and can have lots of bursty workloads and incomplete runs, to training, where you're literally spending hours and hours with an intended outcome, and at some level, an at stakeness for that data to be correct when it's done. And then the job of inferencing and literally harvesting all the investment in the training by creating returns on the inference lookups that answer a question, basically, whatever that might be, whether it's visual image recognition or speech recognition or looking for patterns. But in today's world, and you look at how all that software is actually deployed, it's across a very broad set of deployment environments. And that's where we're starting to see what we think are 4 key challenges with AI deployment on GPUs. Centering around challenge number 1, just the overall design and provisioning of the accelerated infrastructure, followed by the challenge of integrating AI applications into an existing deployment process that perhaps may not have been as agile as developers and their business teams are expecting it to be today. Also, and I think really relevant to this audience, is fine-grained monitoring to be able to meet application SLA and GPU utilization, and then scaling those deployments out so that you can reliably predict whether you can handle a given workload or whether you need to schedule or look at increasing capacity, or potentially outsourcing, bursting to the cloud in some cases where that makes sense. So to speak more about fine-grained provisioning, Adam's really going to be our expert. I'm sort of where that little green button says read explainer blog, that's actually now Adam Tettleman, who will pick up from where I'm leaving off and so speak to this slide and the rest of his slides that he's got prepared. But in a nutshell, the thing to know about Meg is that instead of just sending a job to a GPU and potentially risking that you're not using all of that GPU's resources, we're actually carving the GPU up into sub-instances, up to 7, that allow for a single A100 to have dedicated stream multiprocessing its own memory, an L2 cache, and sufficient bandwidth for hardware quality of service and isolation. You can actually build services on top of these capabilities that weren't possible before. And so it allows for a much, I think, more graceful means of scaling, better guarantees of quality of service, and obviously the other benefits that come with virtualization and come with sub-instancing, which are flexibility and integration. So I will pause there, give Adam a chance to take control, and once again, I want to say thanks to everybody for the opportunity to fill you in as to what's going on with NVIDIA these days.
Thanks, Barton. We'll get it over to you, Adam, when you're ready.
Yep, and of course, a plane just flew overhead right as I was unmuting. So, can you guys see my screen okay?
Yeah,
Okay.
take it away.
Cool. Well, thanks, Barton, for the introduction. So again, my name's Adam, and I'm a solutions architect. I actually worked on a lot of the projects Barton brought up. So some of the automation tools, the infrastructure tools that NVIDIA develops. I'm involved in a lot of those projects. But today I want to focus on MIG. So Barton just gave a good sort of high-level overview, and I think I'm going to try to do a more technical deep dive sort of engineering talk. So hopefully everyone here is excited for that. And I'm just going to talk about what MIG is, some of the technical details, and how you can and why you would take advantage of it. Let me just get this set up here. And I'd also say that at any point, I'm kind of looking at the chat. So if you have any questions or anything like that, feel free to put those in. I think we want to have the time for QA at the end of this conversation. So first off, what is MIG? So Barton gave a good introduction, but the crux of it is that a lot of GPU workloads don't require a full GPU. So if you're like doing something like a demo, or you're building a POC, or you're testing even a small AI model or a lot of HPC workloads, you don't need that full 40 gigabytes of GPU memory on the A100 GPU. And so traditionally with any scheduler, or you're going to be deploying your application or running your NGC container, and you have an entire GPU allocated to you, whether or not you're using the whole thing. And if you're a data scientist, maybe you don't care because, well, you're getting your work done. But if you're any of the other infrastructure or operational people, it's a wasted resource. And we really want to take that GPU compute and that GPU memory and make sure that someone is using it at all times. So you're buying these GPUs, you want to get the most out of them. And I've had many customers come to me over the past years asking for ways to split their GPUs. And there's been some answers, like Barton said, there's been vGPU options, and there's been MPS and things like that. But there hasn't been what MIG is, which is the ability to really physically partition a GPU into currently up to 7 fully isolated devices. And so when you present these devices to an application, they're seen exactly like regular GPUs. They're going to have guaranteed QoS, like we brought up. And the really cool thing is that the flexibility is there. So you can reconfigure the sizes of your profiles to meet whatever your demand is for the day, whether you're doing HPC, deep learning, or AI. And there are many different sizes, as I'll show in a second, so that you can perfectly configure it for the workload you have in mind. And I kind of want to reiterate something I just said, which is the workload size. So I know a lot of people in the space are probably doing large workloads. I think on the first slide that Rob showed, it had 33% of jobs were using MPI, something like that. So you won't be using MIG necessarily for that if you're training those large models. It's more meant for if you're doing debugging, you're doing lighter HPC, you're doing development, and then a lot of inference. It's going to be super effective for inference because it lets you get the both of best worlds. And unlike a DGX A100, where you have 8 of these GPUs, you can configure 4 of them for the MPI jobs, the multi-GPU, multi-node jobs. And then you take the rest of them and you split them up into small devices, medium devices, large devices for MIG. So it becomes sort of a universal tool for any of those workloads. So I think this is the same sort of the slide that Barton showed a second ago. And what I want to reiterate is that previous technologies did logical separation, or they did time slicing of workloads. But what we actually have here with MIG is physically dedicated memory and compute on the chip. And that's the technology that was built into both the hardware and the software that really allows MIG to bring this powerful new feature to the A100. So I kind of want to show a video that features what this looks like. So at the top of this video, we're going to have kind of what time slicing looks like now. And then on the bottom, it's going to be MIG. See if this loads. There we go. So work is being done in parallel in both cases. But if you look here as the yellow comes in, it's going to steal all of the bandwidth, all of the memory, and all of the compute of the other jobs, starving them out. So at those periods where the yellow job gets busy, everything else is quiet. And we re-implement the same sort of workload now below with MIG. And we'll see that when the yellow instance becomes very busy, it is going to slow down itself, but it has no impact on the rest of the workloads. So using the MIG feature in this way is going to give you that consistency. You can predict your latency, and the sort of cloud use case, there's no noisy neighbor problem. So you can have more confidence scheduling out workloads to many users, many projects, many teams, because you'll know that they won't impact each other. If someone, for example, were to crash their GPU application, in some of today's technologies, it could impact other users. But in MIG, you can crash an entire device and it's not going to affect other users on that GPU. But so let me go over some terminology. I think I just used a few terms there that are new. So MIG introduces 3 new terms, really. There's a GPU instance, which you might see in the docs as GI, the compute instance, which you might see in the documentation as CI, and then there's what we're calling a MIG device, which is the actual usable device.
Hey, Adam.
Yep.
Somebody just tossed in a question on that last point. So maybe we want to just quickly, his question after the animation was, so the rest of the workload cannot expand into the unused yellow dedicated GPU. And I think that's down to what. So
yeah, that's going to come down to how you configure it. So what we had on the left there was we had, what was it? 1, 2, 3, 4, 5 different applications, right? We had each one of those colors represented an application. And what we did ahead of time was say, each of these applications gets this much GPU memory and this many CUDA cores, and you are not allowed to go beyond it. And so those applications can run knowing exactly what compute they're getting, knowing exactly how much memory they have access to. And if one of them needs more, it's gonna need more processing time. And if that were to become a problem, what you could do is take a small maintenance window, reconfigure it, and say, okay, we're going to give the yellow process more resources, and we're going to take some resources away from something else. So you would end up with less MIG devices, but each one would be maybe a little bit bigger.
Thanks for that.
And yeah, and so I was going to say more about this later. I've got some slides, but the cool thing is that operation I just described, it can be done without impacting running workloads. So you would basically pause the yellow job, pause the blue job, remove the device from the blue job, grow the device from the yellow job, and then start the yellow job back up. And you could do that all without impacting any of the other running jobs. So the reconfiguration is lightweight, and as long as your scheduler is reassessing what resources are available, you're all set. And so the 2 things that I just said here, and these are the sort of toggles that you get to play with. There's the GPU instance, which is going to be your top level object. So that's what actually encapsulates all of the physical resources. And then you're going to have your compute instance, which is inside the GPU instance, and that's going to further separate the compute. So it's the pairing of a compute instance and a GPU instance is the MIG device. So the MIG device is what you actually give your application. So it's a collection of GPU memory and compute kind of in a box. And the special thing here, and I think for a lot of people on the call, with HPC applications, you sometimes want bits and pieces of that application to have dedicated compute, but they might need to store GPU memory. And that's sort of what the compute instance is for. And I've got some pointers to some documentation at the end of this that goes into that more detail. And then, of course, lastly, I think I have some terminology at the bottom here, but profiles, there are a bunch of profiles that determine sizing. So we set up to 7 devices, but you can have 1, 2, 3, 4, 5. There's 5 different main sizes of a MIG device on the A100. And as we roll out with new GPUs, that could change, and it's all going to be for whatever you need at the given time. So to kind of summarize that, I've got the 2 pictures here. A GPU can be, or an A100 GPU can be subdivided into multiple GPU instances, and each GPU instance can be further subdivided into multiple compute instances. And that will create a MIG device that behaves just like a GPU device in your application. And so your applications can use a GPU device or a MIG device, and it doesn't really matter because the application will just see it as a CUDA device, so that your app or your framework never even has to know it's running on MIG, which is really cool. There's going to be no change to any of your application code. It's all in the sort of scheduling layer. So this just a few more points here, but when you're sizing this up, typically what you're going to want to do is you're going to want to consider how many users you have and configure that many GPU instances. And this is because everything within a GPU instance is a dedicated hardware. So any compute instances or something that are subdivided into a GPU instance, they're going to be able to talk to each other. So you don't want to give out different MIG devices within the same GPU instance to multiple users. You want to keep those isolated. And of course, doing any of this reconfiguration requires root privileges. So not just anyone can jump in and play with these toggles. So a few restrictions to keep in mind, though, is that if you're doing multi-node or multi-GPU, so if you have multiple compute instances, CUDA IPC is supported. They can talk to each other, but things like RDMA are not, or GPU direct storage, any peer-to-peer stuff, that's not really going to be supported. And a CUDA application can only use a single MIG device. So if you have some applications and you're doing multi-GPU, those will not port properly to use multiple MIGs because that just isn't supported as of CUDA 11. And so that covers the basics about the kind of new components and new terminology that we've introduced into the GPU world. So we've got memory slices and SM slices, which make up these instances. And we've got, again, a doc here. There's a really cool technical document that shows the layout of the chip and how we've been able to kind of segregate all of the components to do this. But one other thing to mention is that you do lose some performance when you enable MIG mode. So there's 8 usable GPU, or there's 8 memory slices and 8 SM slices, which is just a bulk of compute. But with MIG mode enabled, you can only use 7 SM slices, and that last SM slice ends up being used for some MIG overhead. So if you are doing workloads that don't require MIG, it's perfectly fine to keep MIG disabled. So I said before, if you have a DGX A100, right, and you have some very large workloads and then you have some very small workloads, you keep MIG disabled on some to get the peak performance, and then you enable it on others to do your inferencing or your developing or your debugging or your profiling. And that way you can really maximize your utilization. And if you do use all of the small instances, you get up to 56 devices on an A100 or DGX A100. So it's a lot of individual developers doing something. So taking a closer look at some of these sizing options here, there are 18 distinct configurations. So you can kind of see them pictured here. So you imagine you take the top left and you move your way down, and that's your full bar. So up to 7 on the bottom, or 1 on the top, or kind of 3 as we have laid out here. So lots of flexibility. So in this example, we have 3 applications shown in green. So we have a 1 meg device with 20 gigabytes of memory, one with 10 gigabytes of memory, and then one with 5 gigabytes of memory. And these are the profile names, by the way. So I like this chart better. It's a lot easier to see than the other one. But so these GPU instance profiles, they're named after the number of SM slices they have and the GPU memory available. So the 1G 5GB has 1 compute slice and 5 gigabytes of GPU memory. And so as you can see here, you can have a single meg device using all GPU resources, like I said, or up to 7 with no decoders or anything like that, but 1 GPU slice. And in general, what we've been seeing, and I think what I'd recommend, is inferencing and development work should get the smallest profile, whereas HPC workloads and deep learning workloads, you're going to want to allocate based on the amount of GPU memory that you think is necessary for that workload. And so if you have a list of applications, that's the sort of thing you're going to want to look at to determine how to configure your cluster. And speaking of configuring your cluster, this is sort of what that works like. So as you configure and reconfigure, and as your team grows, as your project grows, changing up your resources isn't really a problem. So the first time you turn on MIG, you have to reset the GPU, so that's a little bit disruptive. And it basically, you just click a button, and then as soon as you can, you recycle a GPU when nothing's on it. But once you've done that, you can configure and reconfigure, and this diagram kind of shows what it is. It's not going to have any impact on running workloads. So you can have 4 things running on the GPU, like I said, shut 2 of them down and grow that, and then you have 3 things, and you never had to touch those other 2 jobs. And you can do all of this through NVIDIA SMI, and it can even be managed in a Docker container if you don't want to give someone sort of root access directly on the box. And so speaking of Docker, I don't necessarily want to spend a lot of time on this slide, but Docker is fully supported with MIG and fully supported with NGC. And so if you've done anything with GPUs and Docker in the past, the syntax is almost exactly the same, except for instead of specifying the GPU device, like I think I have on the first one here, you say device equals 0, you specify the GPU device and the MIG device. So device equals 0 goes to device equals 0:0. So no real change there.
I'll put a plug in here now for Bill Bryce's blog article talking about Univa Grid Engine with NVIDIA Docker. So we can point to that later. But there is a nice article on their website that talks about this as well.
Yep, definitely recommend that. So I want to close off, as I always like closing off, with a few examples and use cases. So there's lots of things you want to use this for, but there's sort of 2 or 3 main ones, and I'm going to go over them real quick with some slides. So the first is basic deep learning configurations. So if you're doing inferencing, development, fine-tuning, and training, when you're doing development or inference, we're going to recommend that 7 GPU instances, or sorry, the 7 MIG devices to maximize the number of resources you have, because that's lightweight. When you're doing tuning or maybe light HPC, that typically takes 10 gigs, 20 gigs of GPU memory. So we recommend those profiles. And then typically when we see people training their models, it requires a lot more, and we recommend the bigger MIG devices. And then, of course, in a cluster, you can dynamically resize all of this to fully utilize what you have. And one of the things I've heard people doing is they'll run in sort of a development mode during the day, and then at night they'll reconfigure it and they'll get all of their jobs going. So during the day on an A100 you have 7 devices, and at night it's reconfigured to have 1 or 2 or 3, so you get all of your training workloads done. So you come in the morning, you look at your results, and you're ready to get going again. So that's a really cool technique that I've seen people do. And then here's just sort of an example of what a mixed workload would look like. So in this configuration, we have 3 GPUs, or we have 3 MIG devices, 3 GPU applications. And so there's a GPU instance 0 on the left here with 4 containers, each with their own MIG device. It's probably like a deep learning pipeline. Then in the middle here, we have an HPC application LAMP. It needs more compute, but it doesn't really need a whole lot of memory. So that's got 1 larger MIG device. And then on the end here, we have our 3rd GPU instance. And this is just someone running like a CUDA debugger to try to figure out why their kernel isn't behaving properly. And they just have the smallest MIG device. So last 2 things I want to talk about are sort of the same configuration, but different use cases. So I mentioned inferencing before. And what we see is that many AI applications are already doing inferencing. And I'm sure some of you on the call are familiar with this. And typically we'd like to see people do large batch inferencing and take full advantage of parallelism and the GPU. But we see a lot of people doing small batch inferencing, batch size of 1 even. And then in these cases, you really don't leverage the GPU as much as you should. But if we break the GPU down into 7 small devices, all of a sudden that 1x performance becomes 7x performance. And we've even seen that a single MIGlet, or the smallest MIG device, is as performant doing batch size 1 inferencing as an entire V100. And so you pair this up with Triton, which is another solution we have for inference, and it can take advantage of the GPU, and it can take advantage of multiple MIG devices. And that's just a really effective way to boost your inference speeds without really doing any work. The other cool thing about this too is that if you are running an internal cloud, a lot of times you want to, or cloud native architectures demand isolation between customers or between applications, or however you have it set up. And so you intentionally decouple services. And so running a single Triton server to manage everything isn't really ideal. But if you have multiple Triton servers, each with their own MIG device, you end up with a platform that is decoupling the hardware from the software. So it makes it more cloud-like, which is good for a lot of applications. And then lastly, there's the development case. And I think that's what a lot of people here are going to be excited about. So MIG tailors itself to the use case where GPUs are in high demand. And as someone who does a lot of demos and a lot of teaching, and I'm involved in a lot of Deep Learning Institute and Jupyter Notebook work, this one really excited me because it allows you to do these kind of small trivial tasks, but at scale. So if you're doing like a classroom filled with students, or if you've got a bunch of interns doing the first CUDA kernels or things like that, you don't have to give them their own workstation or their own GPU. Instead, you come in, you have one server, you configure it with all of these MIG devices, and all of a sudden I can have 56 developers all on a single server with their own dedicated GPU for learning and developing and for training. And putting the most realistic use case is really that you're doing all of this at the same time. And one of the fantastic things about the A100 and of MIG is that it's possible. It has so much versatility. So I have pictured here that DGX A100 I've been talking about, where the 4 GPUs on the left are doing multi-training or multi-GPU training. The 2 GPUs in the back are doing analytics and machine learning. And then the 2 GPUs in the front are split up into 14 MIG devices, all doing inference. So MIG is really powerful. And just to close, it allows you to take a single GPU and do any workloads on it, big or small, and kind of reconfigure that dynamically to up to 7 devices on a single GPU. So the flexibility of MIG makes your GPU go farther, and it adapts as your use cases change. So I'll take a look to see if there's any questions. I know I was just talking for a long time.
All right, Adam. We'll get to some questions at the end. I think Bill's going to shorten his up
Okay.
to about 10 minutes and start now, and then hopefully we get 5 minutes for some panel discussion and questions at the end. Over to you, Bill.
Okay. Let me
And thanks, Adam. That was great.
All right, can everyone see my screen?
Yep, carry on.
Okay. So I'm going to go relatively quickly because given the time constraints we have, but as you can see from the agenda, talk a slide about the challenges of using GPUs with Grid Engine and really about the applications and GPUs, get into how Grid Engine requires sort of metadata information to make decisions about GPUs, GPU binding, environment, accounting, putting it all together, and upcoming improvements in Grid Engine. So if you look at Grid Engine from a very high level, what it's doing is many different sort of small subtasks in order to achieve the goal of running your application. And when you look at it in perspective with GPUs, you typically have to start with an application, something you want to run in a Grid Engine environment, like TensorFlow or something similar. And then there are other aspects here, which I'm not going to go into a lot of detail, like the metrics, but the metadata, you know, giving the scheduler enough information so it knows that there's a GPU there and what to do, that's important. The arrangement of the GPUs and the CPUs, the topology, the environment that they require to run the application, the containment of it when it's actually running so it doesn't consume more resources than expected, and finally the accounting. So in most cases, you can just run an application by just submitting it to Grid Engine. In fact, all workload managers work this way. They can run scripts, they can run pretty much any binary executable. But it's more complicated when you move into a GPU type application or framework because these things require a lot of other tools. There's many other dependencies. There's a lot of sort of software around it. And in response to that, a lot of people, you know, took the pragmatic approach. They did the obvious things. They figured out ways to package the applications, to virtualize them and containerize them. And a lot of, you know, these frameworks rely on many other open source tools to work well. And so making the choice of which way to do it, you have different variables. You could use modules to do it, which is sort of like a well-known way of changing your sort of environment to run these types of applications. You can use Python virtual environments. In fact, lots of these tools do this already. Or you can use containers. And we'll talk a little bit more about containers in this presentation, and because that is sort of the natural flow of doing it with Grid Engine. So what are containers? Well, I think by now, I would say everybody on this call knows what a container is. But what's really interesting is that, and this is directly from the Docker website, the most recent up-to-date one, is they moved away from saying that it's, you know, like the be-all, end-all, you know, does all your song and dance and is the reason why microservices exist and things like that, and gotten down right to the point that it packages everything up. It packages everything up for your dependencies into an easily distributable package so you can take it and move it somewhere else. It takes your application and makes it portable. And that's really important because when you're doing things like running an Grid Engine cluster on-prem or running in a cloud, you need that application to be portable. So that's what Docker or Singularity are providing for you. And in fact, as Rob already mentioned, Singularity is quite a lot more popular in HPC environments due to one of the obvious reasons that Docker requires a Docker daemon. And that makes it not quite fit as well with most workload managers, although in Grid Engine, the way we integrated made it so that it is quite reasonable. But both tools are typically used in HPC environments. And if you want more information, you can always go to Docker.io or scilabs.io to find out more detail. So how do we take these container images and connect them to Grid Engine? Well, first of all, you have to choose the container images. You have to find them, find your application in those registries, and then determine if they will work for you, and then use them in your Grid Engine cluster environment. There are various ones out there. I've just given a few here. Docker Hub, Singularity Cloud are common ones people know about. However, I suggest if you're going to really do GPU-based you know, applications and framework, you should consider NVIDIA NGC It has a catalog of GPU optimized software for HPC, AI, ML, deep learning. Lots of the things that Adam talked about are already in there. They're already container images, and they're optimized for the GPUs. It's a good place to start. So once you've gotten to the point of, I've got my application, I know what I'm going to do, I found a container image that I can use within my cluster environment for my GPUs, I now need to configure Grid Engine to tell it that the GPUs exist and how they are arranged in my cluster environment. So right now, GPUs, they must be modeled in Grid Engine. It's not automatic, although frankly, that is something I would like the engineering team to do, to automatically figure out what the RS map should be for GPUs. And what RS maps are, as you can see from this slide, is it's really an enhancement to Grid Engine to provide a host-based, what we call a consumable resource complex. Probably didn't tell you much, but basically it's a way of describing, putting labels on the GPUs on each host, and then allowing those labels to be used by the scheduler so it can allocate jobs to those GPU resources. So, as you can see, you can request one or more of these when you're submitting your work into the system. And so to use it, you have to initialize it first. And the reason I'm explaining this is because we've recently added functionality so that when you're initializing it, you're telling Grid Engine, what is the CUDA ID of the device and what is the device file of the device. And this is important because this will allow Grid Engine to correctly allocate the proper GPU to your application when you're submitting your job. You don't have to really worry about it. You don't have to say, oh, I'm submitting my job and I'm going to use, GPU, 0, and then someone's going to use GPU 2 and 3. That's sort of like manual scheduling. You'd want the Grid Engine to do it, and as you can see, submit a job just saying GPU equals 1. And what will happen is the scheduler will choose the available one that's free, not being bound by something else. You can see how it's been granted to you, so you know which one you've got. The job itself can discover what GPUs it was assigned, and that can be done in two ways, using R variable, which is that SGE HDR thing means Sun Grid Engine, host granted resource, that's what it means. Or you can use CUDA visible devices to determine, what GPUs you've been assigned. This can also work all together with Docker and with C groups. You can combine them together. So you could have quite sophisticated job submissions, submissions where your application, runs in a container, which is limited by a C group. And at some point in the future, also limited by what make you're running on, but we'll get there. Another slightly important aspect, depending on your type of application, is the topology or arrangement of the GPUs based to the CPUs in the machine. And again, you can tell Grid Engine how that's arranged, and that's what this is. Here you can say, for example, I have 2 GPUs, and the first GPU is really closer to the cores on the first socket, and the second GPU is really closer to the cores on the second socket. Naturally, this is an artificial arrangement, but that's the basic idea. And so, as I mentioned before, in conjunction with C groups, with GPUs, with Docker, and binding, you can put it all together to really nail down exactly where you want your application to run and enforce it. So we talked a lot about topology. We talked about the, finding the application, choosing the container technology. Now we're going to talk a little bit about the environment and containment. So to make things work well in a Grid Engine cluster with GPUs, you need GPUs, you need the drivers, you need Docker, you probably need the NVIDIA Docker 2 subsystem, or I think it's already installed now in the latest version, and optionally NVIDIA DCGM. So if you have these things set up in your Grid Engine environment, and then you submit your job, Grid Engine needs information to figure out, what GPU CUDA ID it should assign to the job. As I mentioned, that's given to you, the SGE HDR. And then also working with C groups. And all of that is achieved using something like Docker or Singularity. So you'd see something that would look like at the bottom line there, where I'm saying, submit my job, make sure it runs on a machine that has Docker, make sure I have the NVIDIA CUDA Docker image, make sure I have 2 GPU, and I'm using the old syntax here with runtime NVIDIA. The new one is different, and job.sh. Other things that are important is that you saw at the top of the list of things I was going to talk about is accounting on GPUs. This is a recent addition to Univa Grid Engine. I don't know if many of you have tried it out, but you can optionally turn on GPU metrics collection. And that's with an execution daemon parameter, as you can see here, enable DCGM job usage. And then you can tell Grid Engine what metrics you want to collect, because there's actually quite a lot of metrics that DCGM collects. And some of them may be useful to you, some of them maybe not. Some of them may just, if you collected them all, it may just be too much in your accounting file. So you could say, collect them all, or collect things like energy consumed, max GPU memory used, overall health. So you have your flexibility on how you want to configure the accounting. So I know I went through this pretty fast, but I wanted to give you a high-level overview. So the basic workflow, basic idea are, let's recap. You choose an application. You got to choose what kind of technology to use for your containerization, Docker or something else. Choose the hardware. You can use a GPU on-prem or even in the cloud if you don't, for example, have an A100, because some of the cloud vendors do have them. Optionally, you choose an image with NVIDIA drivers and Docker, or you can create your own image. That requires a fair amount more work, so I suggest you start with an already pre-existing image. If you're creating your own image, you got to make sure the drivers are installed, Docker is installed, NVIDIA Docker 2, depending on what version of Docker you're using. Configure Docker for NGC, not very difficult. Configure Grid Engine with RS maps for GPUs and add this cloud complex. And when you're done, you have it all packaged up. And so you should be able to submit an application into Grid Engine and tell it, give it a resource complex attribute like -L cloud, that it will run in cloud versus running in your on-prem environment. Now, given the time constraints we have, I would like to tell you a little bit of what's happening in Grid Engine and what's coming related to the A100 and MIG support. So in less than a month, we'll have 8.6.16, and it will have support for A100 and MIG. This is the initial support, and DCGM 2.0. So what we added, first of all, was an obvious extension to support the --GPUs flag in our Docker integration. And that is the new syntax for basically telling Docker that you need a GPU inside your container. And there's more details on how that flag works, but it works exactly the same way as it does with the Docker command. So you can do things, as you can see here in the example. Again, give me a machine with Docker, give me one that has the good images, make sure I'm using the latest Docker API, and then give me the GPUs and the specific device. And you'll notice here, we are supporting the similar syntax that NVIDIA is supporting for referencing the GPU and the MIG. It's like 0:0 means, GPU ID 0 and MIG ID 0. So similar type of syntax is used. Of course, we're escaping it because of our parsing. One important thing to remember is in our integration right now, MIGs are not directly requestable, but because you can configure them in the RS maps, you ultimately are able to select them. So really the RS maps and Grid Engine represent the underlying MIG. We've also added a Docker resolve CUDA ID true, and that enables the functionality to handle the MIGs properly. And what that does is provides another slight improvement to the way we do things, allowing you to let Grid Engine choose the GPU and the MIG directly. So that first example, that was like myself. I was just choosing it. I wasn't letting the scheduler choose it. But below here, with this syntax for $GPU 0, what will happen is the Grid Engine scheduler will choose the GPU ID and the MIG ID and replace it. And so it will work correctly as you expect. And then one last thing is in 8.6.7, which is Q1 2021, Grid Engine will automatically detect MIGs on a machine and that MIGs have changed. So if someone changes the MIG configuration, the execd will detect it, but it will not automatically create the RS maps yet. And that's, I think, the last improvement we'll do for a good start at MIG support in Grid Engine.
Thanks, Bill. Appreciate it. What we'll do now is we're right at the top of the hour and we're going to start losing people. So let's get to a few of people's questions and then we can wrap it up. So first off, there was a question earlier about the number of people in that survey I showed. That was a very small survey, so not necessarily statistically valid. It was about 40 respondents, so could be skewed one way or the other. And it was to our customer base, so it's skewed in that fashion for sure. Question from Skylar: are there plans to ship lower tier GPUs than the A100 with MIG support? To Adam or Barton?
Yeah, so the plan for MIG support, as far as I know, is it's something built into the Ampere architecture. So we should expect all of our future chips to probably support that, but no official word on when any of those are coming out.
Okay, thank you. And then Monica is asking, can the MIG feature be used with cloud infrastructure like Oracle Cloud that already has A100 GPUs? I assume that's yes.
Yeah, so in cloud environments like AWS or GCP, where you're getting a full instance, you'll be able to take advantage of that. And then in Oracle, and even if you have your own cloud on-prem, there's technologies that will allow you to take advantage of that.
Another question that came in: how do I turn on MIG and configure MIG?
So we've got more resources on that. I don't want to go into too deeply, but there's a few NVIDIA SMI commands.
SMI commands, okay, cool. Do I need a special container stack to use MIG? I think we sort of addressed that, but maybe someone could just reaffirm that one.
I would always just recommend use the latest NGC containers for optimized GPU code.
Right. And then for DGX OS customers, it's already built in.
Right. I'd use the latest container images from NGC for sure.
Yeah.
I would also make sure you're on the latest. If you're using Docker, use the latest Docker, especially because it adds that GPU flag as well, which makes it much easier to do things.
Yeah, I'll just also add, this last week we've added certification to NGC, so there is a framework for being able to certify that the containers have been tested at a specific level of functionality and capability.
A couple last questions. One's asking open source driver. I assume that's a question as to whether the driver is open source. Please clarify, Jonathan, if that's not what you're asking. Adam or Barton, you know,
yeah, I'm assuming that so I don't believe the NVIDIA driver is open source, but it's freely available on our website.
Gotcha.
Yeah,
thanks, Jonathan.
The driver's not open source. We participate in open source projects. An example of that would be Rapids. And then the bindable libraries are redistributable that you would use to develop applications. So you would use include files and libraries to build an application, and developers are authorized to redistribute those pieces, but the driver itself is still closed source.
Gotcha. And another question is, will the slides be sent out? So I know we're recording this and resharing that, so you'll certainly get them that way. We'll confirm whether we're going to send out the slides afterwards. I don't have the answer to that one in PDF form. Okay, I think that's it for questions. I really want to thank Barton and Adam from the NVIDIA side for the great presentations. They were very deep and informative, and I think people will really value that. Thank you, Bill, for your session on how Grid Engine interacts with all this cool stuff that Adam and Barton were talking about. We really appreciate you all attending, and we will see you next time.